Hello everyone. In this presentation we're going to walk through the 4-gas meter that we carry. It's the Industrial Scientific MX4. You'll notice this is a second upload. First one apparently had some problems with the actual successful recording of audio. So this will be a short presentation, about 15 minutes or so, just walking through our gas meter and what's on it and how it functions. So the gas meter we carry is called the Industrial Scientific MX4. It has 4 individual sensors located in the upper part of the machine with a big screen down in the lower part where you have readings of each one, and nice and easy operation with a power button and then a basically enter and screen cycle button. The meters we carry, they have this unit up on the top. So the meter looks like it kind of stops and there's this thing attached to it. That's called an aspirating pump. That allows you to draw air in through tubing versus just having to wave the meter about in the air. The advantage to that is we can be more specific, make sure we're pulling in air from where that hose is ending up. So if you want to sample specifically above a liquid, you can do that. Or want to sample into a room before you go in, this does a good job pulling air through. The risk is if you add length to that tubing, you can ruin, it takes a lot longer for the sensors to read. So the sensors we have combustible gas, so that's percent of the lower explosive limit of the gas mixture. We sense percent oxygen and parts per million of hydrogen sulfide and carbon monoxide. We'll walk through each of those in a few minutes. Yeah, MX4 is a great gas meter. We love using it. It's nice and easy to use. Good for both industrial and fire service use. Strongly recommend it. The combustible gas sensor reads in the percent LEL, a percent lower explosive limit of the gas mixture in the air that it's sampling. The way that this works is there's a little catalytic sensor that heats the air and tries to get it to combust. And the more effectively it can get the air to combust, the higher percentage of the lower explosive limit is present. It's important to note that this meter won't read greater than 100% of the LEL. So for whatever the gas mixture that's present, it won't get above 100%. This detector will read methane, propane, octane, butane, nonane, any combustible gas, and therefore it can read gasoline and diesel vapors as well, because those are gas phases. It's obviously combustible gases are flammable if in the right range. They can also explode if they're properly confined and have the right mixture of oxygen present. They can also be as simple as asphyxiant. Obviously, if there's too much methane in the air, there's not enough oxygen, therefore you can't breathe. Lower problem priority, arguably, in the flammability and explosiveness, but that's present. Some are also toxic and can have a narcotic effect. So if you're exposed to them over a significant amount of time, they can have some significant toxic or even cancer-causing kind of end results. So the two combustible gases we're most concerned about are methane and propane. Methane is the primary ingredient in natural gas. Often there's a few other things mixed in because it's really not that refined. It's just literally the gas that's natural that comes out of oil wells. But methane is the primary component. That's CH4, 1 carbon, 4 hydrogens. Specific gravity is 0.5, so it's lighter than air. It'll rise in rooms or other spaces, and it tends to rise away from whatever space you're in. So don't find it accumulating anywhere other than in the high parts of a structure. It's explosive between 5 and 15% in air, but that's arguably more complicated than it seems. So what actually exists is there's a range, there's an explosive range with the mixture of air that's present where there is the right blend for that gas to explode. This is present for any combustible gas, any mixture like that. What we have is a range where it can be either too lean, explosive, or too rich, or you have the range where it has no explosive potential at all. So just because you're at 10% methane in air, if you're at 0% oxygen, obviously it's not going to catch fire or explode. That's just not possible. So if you don't have enough oxygen to sustain the fire and actually initiate that combustion, the gas isn't combustible. The flip side is also true. If you have too much methane present, too much propane, anything like that, the fuel mixture is simply too rich. You won't actually have enough oxygen present to start and sustain combustion, and you can't have a continued chain reaction. So what you end up with is what's called the Coward's triangle or Coward's diagram, named after a researcher who a few decades ago was working on coal mine fires and coal mine explosions. Particularly started with methane, but this can be created for any gas. So what we see is a 2-axis plot of oxygen here on the y-axis and percent methane here on the x-axis. That can be any particular gas, but we're looking at methane specifically here. So our quoted upper explosive limit, 15%. Graph's a little off, it got shifted. Percent lower explosive limit right there, about 5%. So anywhere where there's less than 5% is going to be too lean or simply isn't possible to explode. So right here or right here. Or once we're in that range, it can either become too rich as the oxygen concentration comes down, or you have kind of this Goldilocks zone where the gas is explosive. This is available for any combustible gas. You're able to either compute this or look at a chart from research. It's also important to note, obviously you can't have more than certain percentages. You can't be more than what oxygen is actually present in the atmosphere because there's still a lot of nitrogen in the atmosphere. So be alert, you can still be in that range, but if you have no oxygen present, then you can't still have an explosive mixture. Propane, C3H8, more common in rural areas. It's what's used for heating and cooking out there. Specific gravity is 1.5, so it's more dense, it's going to sink to the ground, it can hang out in low spaces, and it doesn't disperse as easily. It's explosive between 2.3 and 9.5%, so it's a bigger triangle. You'll see a bigger region on the Coward's diagram, but it is still an explosive gas, and it's actually a little bit more hazardous in that realm. So let's be a little more specific about what the gas meter actually reads. Gas meter is reading the percent of the lower explosive limit in the air. That's the percent LEL. So 5% of methane in air is 100% of the lower explosive limit. As we approach that, obviously our percent LEL is increasing. Our low alarm limit on the meter is set at 10% of the LEL. So 10% of the lower explosive limit, so 5% in volume. What is that? That's going to be about 0.5% of the volume in air. So not a whole hell of a lot, but it's still a pretty good first indicator that we're starting to see some kind of problem. High alarm is set at 20%. So as soon as we get more than 20% of the LEL, that means we're being very concerned, very conservative about what's going on. Think about being on air as soon as you cross that 10% lower alarm limit and know that something's going on. As we get closer to that 20% mark, think about making sure that we're doing something about ventilation or controlling the source of that flammable gas, be it shutting off the supply to the structure, starting to open windows, things like that. The risk is we're reading 20% at the entrance to the structure or a little ways in. We're not all the way through. We don't necessarily know what the readings are for the whole structure. Obviously, if we've walked the entire thing and the highest we see is 20%, no big deal. But the risk is we start to see that 20%. It could be 100% further deep into the structure as we go. So there is still that explosive potential as soon as we start to get into that range. What's important to know about operating the meter is when you hit that 100% of the lower explosive limit, you need to turn off and turn back on the meter. It wipes out the sensor as soon as you cross that 100% range. The way that the sensor chemistry actually works and the way that it actually detects gas, as soon as you cross that 100% threshold, it's no good. So you have to, if you hit 100% or cross in over 100%, you need to back out, obviously ventilate, do something about the threat. You also need to turn off and turn on the meter again and clear out the memory of the sensor and give it a chance to restart and recycle. That's super important because you could just be in that 100% over range. Your ventilation could be effective, but you don't know that. Or it could be getting worse and you don't know that. So make sure to restart the meter if you hit 100% of the LEL. So let's talk about the oxygen sensor. This reads in percent volume, resolution of 0.1%. Oxygen is obviously required for life and combustion, we know that, and normal atmosphere is going to be 20.9%, but it is important that you do a fresh air zero. The oxygen sensor isn't really a percent of the total mix, it's detecting the true amount of oxygen present in the air. So when you start this machine and you do that fresh air zero, it calibrates the actual reading of oxygen in the air to the percent mix. So what this means is that it's sensitive to changes in barometric pressure. If you were to travel a great distance, especially going up and down in elevation, more than even 1,000 feet or less, you can see changes in the oxygen reading pretty easily and pretty significantly. This is important to know and be alert for. Just simply, you could be seeing a low oxygen environment and you could be seeing problems like that, when in fact everything's fine. You just changed in elevation, so therefore you changed in barometric pressure. So normal atmosphere 20.9%, but you do need a fresh air zero. Oxygen can be displaced by other gases. So if you start to see symptomatic folks, some kind of sick building syndrome, anything like that, be alert if that oxygen sensor reading is starting to come down. It's normal for there to be variation around that 20.9 mark. Simple wind, things like that. There can be any number of weird variations that give you a few tenths plus and minus off of that normal. But as soon as you start to see something change and it's coupled with some kind of symptoms or some kind of issue going on, be alert that something's up. Our alarm limit's 23% at the high end. We don't want to be in super high oxygen environments. And then on the low end is 19.5%. Anywhere in there, we as humans are pretty good to breathe, no issues, nothing like that. And that's a good tolerance range for what would be normal variations in air. So the carbon monoxide sensor reads in parts per million. Obviously, carbon monoxide is more toxic than oxygen, where oxygen is necessary for life, carbon monoxide is toxic. So we're being a lot more sensitive to what we're seeing. So parts per million, 10,000 parts per million is equal to 1%. So we're reading a lot finer than we're reading with oxygen or even percent of LEL. Carbon monoxide is toxic. That's its primary risk and really what we need to be concerned about. But it can also be combustible. It's up at a pretty high range. It's not something where I'd worry about it on a day-to-day basis, but it's something to be alert for. It's also most significantly colorless, odorless, and tasteless. So you could be in a high carbon monoxide environment and have no knowledge of it other than actual physical symptoms of carbon monoxide poisoning. Carbon monoxide is produced by incomplete combustion, so be it a furnace, water heater, fire, anything like that, you expect to see carbon monoxide. Unless it's a super clean burn where you have a very good fuel-air mixture, carbon monoxide is going to be produced by any fire. So our limit values and what we see from a regulatory perspective, the threshold limit value time-weighted average, so you can be exposed to an average of this value for 8 hours a day for a working career with no ill effects, that's 35 parts per million. The absolute ceiling value, even if it averages to less than 35 parts per million, you shouldn't be exposed to more than 200 parts per million of carbon monoxide at any one point in time for a regulatory perspective. Then the immediately dangerous to life and health, or IDLH value, is 1,200 parts per million. If you're exposed to more than the IDLH value of any given gas or any given environment, that presumably means it's either enough either to render you unconscious and unable to escape, or to cause sufficient irreparable damage that it's going to be a lethal exposure. So 1,200 parts per million. Start thinking about being on air as soon as you cross that 35 parts per million. It can get higher, it can be more significant, and it's not a big deal. Up to 100-ish, nothing to panic about, but start thinking about being on air. Remember, it doesn't cost anything to refill air bottles. That's not a big deal. But obviously, if you're crossing that 100 mark, getting close to 200, or even getting anywhere near 1,000, you should be on an SCBA, be totally isolated from that environment. Hydrogen sulfide also reads in parts per million, but it's a much more toxic gas than carbon monoxide or any of the other gases we've talked about so far. It's produced by the decomposition of organic matter or minerals, has a specific gravity of 1.17, so slightly more dense than air, and it's explosive between 4.3 and 46%. 4.3% corresponds to how many parts per million? A lot. So it's not as significant of a risk. Obviously, the toxicity is much more significant, and that's why our meter reads at 1/10 of a part per million, as opposed to carbon monoxide, where it reads at 1 part per million as the minimum resolution. Threshold limit value, time-weighted average, is going to be 1 part per million. The short-term exposure limit, so a 15-minute duration, is 5 parts per million. Ceiling value, the don't exceed, is 10 parts per million, and then that lethal, be scared, big deal IDLH value is 100 parts per million. So it's 10 times more toxic than carbon monoxide. The good thing about hydrogen sulfide is it has an extremely pungent smell. You can smell hydrogen sulfide down in the 5 to 10 parts per billion range. So you're at 1,000 times less concentration than what would be toxic. You can smell it. So that's very handy until the hydrogen sulfide removes your ability to smell effectively. As you're exposed to increasing concentrations, it damages the nose, and you're not able to smell it as that concentration grows. So just because you don't smell it anymore doesn't mean it's fine. Hydrogen sulfide is one that you think about with an interior odor investigation. Also, obviously think about the odorants in a natural gas or propane. Something called methyl mercaptan is added to natural gas and propane because they're both individually kind of not, they don't smell like anything, like may smell a little bit like organic gases, kind of strange. But it's important to know that they add an odorant called methyl mercaptan. That can smell somewhat like hydrogen sulfide, but hydrogen sulfide is a lot worse. So any interior odor investigation where it's a rotten egg, kind of nasty smell, this is one of the gases to consider, generally from sewage or something like that, but obviously also be thinking about that flammable gas leak. So that's it. That does it. Put any questions down in the description. Got the audio to work hopefully this time. So good luck. Thanks.